calculating cell potentials or from standard reduction potentials. So we have our table of standard reduction potentials. We're going to use those to calculate the potential difference in a cell. So this is the difference in electrical potential, right, in volts between points. The maximum potential difference between the electrodes of the voltaic cell is referred to as the EMF, you'll see, or electromagnetic force. It's called E cell. The electrochemical potential, lots of different words to describe it. The equation that we use, we just sum up so the cell potential is the sum of the reduction half reaction potential and the oxidation half reaction potential. So E naught red plus E naught ox would give me E naught cell. But remember, E naught ox is really just the negative, right? We changed the sign, and we'll see examples of this again in a second. We changed the sign from the reduction potential table to get negative. So you could think of it as E red plus negative E naught red, right? We'd get the same thing, and that's what this equation is. So reduction occurs at the cathode, oxidation occurs at the anode in a galvanic cell. So if you take E naught at the cathode minus E naught from the anode, and these are both reduction potentials, so not changing the sign, you end up with the same answer, right? I'll try to do it both ways. It's not a big deal, but did I say that anions move towards the anode in the salt bridge? I should have. Anodes move to the fluid. Anions move towards the anode in a galvanic cell. Oh, that's actually always true. Anions always move to the anode. All right, cell voltage, electromotive force, cell potential. We can measure this, right, by just plugging in a voltmeter, multimeter, and measuring the voltage. So here's some examples. This is the one we've been drawing, right, our half cell. So what's the oxidation half reaction here? Zinc is being oxidized to zinc plus 2, so that's zinc solid goes to zinc 2 plus 2 electrons. Right? That's the oxidation half reaction. The reduction half reaction is copper 2 gains 2 electrons to give me copper solid. Right? And it's balanced, 2 electrons on both sides. So that's good. We don't need to do any more balancing here, but so let's see, here's E naught red for both. So E naught red. All right, so copper 2 reduction is going to be, let's call this guy E-ox. Okay, so copper 2, where is it? Copper 2 here is reduced to copper solid. That has a reduction potential of plus, and put the signs, 3-4 volts. The oxidation potential of zinc, where is he here, is plus 0.76 volts. So if I add my oxidation potential and reduction potential, I would get the cell potential, which would be plus, looks like 1.10 volts, right? Alternatively, if I just use the values from here, right? So I'm just looking for the value that corresponds to whatever the oxidation or reduction reaction is. I don't have to worry about the direction. Then I use this. So E naught cell equals E naught of the cathode, which is copper 2 being reduced. So that would be plus 0.34 minus E naught of the anode is the zinc reaction. So I would use this minus 0.76 volts. Right? Minus a negative is plus a positive equals plus 1.10 volts is E cell. So either way, you get to the same thing. So you can sort of memorize this. This is how it's written a lot of the times, or just understand that really what you're doing is adding up the reduction potential with the oxidation potential. Let's do another example. All right, so here's the question. Does this go spontaneously as written? Well, first off, let's calculate E cell. So we have to identify the two half reactions. Let's see, iron 2 plus, oh, interesting, goes to iron 3 plus, that's oxidation, so he loses 1 electron. Zinc 2 plus goes to zinc, plus 2 electrons goes to zinc solid. That's a reduction. So here's oxidation half reaction, here's the reduction half reaction. Then we can add them up. So I'm going to do the E ox, E red. All right, not again for standard. So zinc 2 is negative 0.76 volts. Iron 2 is being oxidized, so he is going to be, the opposite of that, negative 0.77 volts. Ow. So if I add these up, I get negative 1.53 volts. All right, so I use this method. You could do this one if you wanted. We get that. We get a negative. All right, the previous one was a positive value. If it's positive E naught cell for a given reaction, it is spontaneous. Right? It is a galvanic cell, galvanic or voltaic cell. If it's negative, it's non-spontaneous. Right? It's an electrolytic cell. We could make it work that way if we plugged it into the wall and gave it some electrons as in the form of electricity. All right, so if you get a positive here, it's spontaneous, negative, non-spontaneous. Let's do this one. Calculate the standard cell potential for a copper hydrogen electrochemical cell. So here's the notation. Copper is being oxidized. Hydrogen ions are being reduced. Oh, this is a platinum electrode. That's an extra thing. There's the salt bridge. There's the concentrations. So let's see. Oxidation half reaction, and then the reduction half reaction. So oxidation is copper, isn't it? Copper solid goes to copper 2 plus 2 electrons. H plus goes to H2, 2 there, right? Oh, plus 2 electrons. Okay, and let's find the value. So E ox. Am I butchering this? I'm butchering this. Dang it. Let's follow through and see what happens. So E, I've written this as the oxidation, and this is E naught red. E oxidation copper 2 would be negative 0.34 volts. And then hydrogen is defined as, oh, interesting, 0. Okay. So E cell is going to be negative 0.34 volts. Is that spontaneous? No, right? A negative sign for E naught cell is non-spontaneous. This reaction doesn't want to happen. So what would actually happen in this case, right, is the reverse reaction is going to happen, right? The chemistry doesn't know which way you've written it on the piece of paper. It just knows where it wants to go. So does copper want to be reduced? Copper ion want to be reduced? Yes. Does copper solid want to be oxidized? No. So really what's going to happen is the reverse reaction. So this is going to be the oxidation half reaction. The reduction half reaction then is going to be copper 2 plus 2 electrons goes to copper. And that will be E naught red of plus 0.34 volts. This guy's still going to be 0, but now if that's a plus, this becomes a plus. So E cell is 0.34 volts. All right. The whole point of this, that I'm doing poorly, is if I built this electrochemical cell and I measured the cell potential, because we've defined the reduction and oxidation potential of the hydrogen electrode as 0, whatever I measure, 0.34 volts, is going to be the reduction potential of that the thing I put in there. So this is actually, they built the table. Oof. All right. Right, and so this is them running the thing. So if you wanted to build this table, you put some aluminum with an aluminum electrode in there, right? Measure the voltage. Whatever you got, that would be the reduction potential that goes in there. Let's see. Okay, we'll leave this one next, sort of step up. So far I've told you which way it's going to go, kind of. Next, we'll talk about how to predict which way it'll go.